Okay, so I'm William Nehrboss. I am a co-founder and head of research at the conversational analytics startup Casca. And today I'm going to be talking about my paper, Casca leveraging role-based lexical cues for robust multimodal speaker diarization with large language models. So I'll start by talking a little bit about the problem that we were trying to solve in this paper. And that is the problem of the poor performance of some of the state-of-the-art and most popular speaker diarization tools in real life. So what we found, what we're trying to solve is the accurate diarization of face-to-face commercial conversations, specifically the conversations between bankers and customers in bank lobbies. And so I was working with a lot of the sort of most popular speaker diarization tools and found that strong benchmark performance tended to translate poorly to these real world applications. And I have an example of a conversation, a face-to-face conversation on the right here that sort of highlights some of the problems. So this conversation has short, it's a short interaction. There aren't many speaker turns. Each speaker turn is relatively quick, and there's a lot of noise and reverberance in the conversation. And because of that, the embeddings clusters of the audio, which is used by most uh, clustering-based speaker diarization tools. Um, there's no sort of clearly delineated clusters for each of the two speakers. And so if you had a naive clustering algorithm looking at this plot, it would be really hard to sort of draw the line between who's speaker one, who's speaker two, in this case, who is the doctor and who is the patient. And so I was thinking through some of the ways in which we could leverage other information contained in these sorts of commercial conversations, specifically role information, the distinction between the roles of the speakers, to potentially aid in the diarization task. So before I get into exactly what that looks like, I'm going to take a quick detour and talk about a little bit of history. So some of you might be familiar with the Enigma machine, which was used by the Germans in World War II to encrypt their communication. And something that I found interesting is that um, when the English were cracking the Enigma machine, something that was really helpful in deciphering the messages were these plain text phrases called cribs, which is something it plays a big role in cryptography to this day. But what they were particular phrases whose meaning could be determined using contextual factors. For example, incomplete messages began with the word continuation. So they're able to map that word continuation to the encoded word and use that mapping to help decode the rest of the conversation. So how does that apply to speech diarization? Well, what we were thinking is, what if you knew that the speaker source of certain phrases within a spoken conversation based on contextual factors such as role distinctions between the speakers? Perhaps you could use that mapping of that speech and the acoustic characteristics of that speech to connect that sort of voice print to the speaker, and then use that voice print to decode, in a sense, the rest of the conversation. That is, assign the spoken audio to the speaker source in the conversation. So that's sort of what we tried to do with Casca. Um, and Casca stands for Context-Aware Speech Classification Architecture. And it's also the name of our startup. So we thought that was kind of funny. But Anyway, so how it works from a really high level, and this is kind of diagrammed here on the right in that medical conversation, is it first identifies speaker roles. So in this case, we're going to have a doctor and a patient in the conversation. And then it identifies phrases within the conversation that are clearly associated with one of those roles. So some of the phrases like, how are you doing today, aren't going to be, perhaps that might be more likely to be the doctor, but isn't dispositive one way or another. But some of the phrases used within the conversation, such as, I'm going to recommend an X-ray in the case of the doctor, or I'm experiencing chest pain in the case of the patient, are clearly associated with one of the two roles. So if you're able to identify clearly distinctions within the speaker roles, certain phrases are going to provide very strong contextual cues as to the speaker source of those phrases. So once that's done, the audio corresponding to those words of making up the phrases that are associated with one of the two roles can be, in a sense, used to compose a voice print for each of the two speakers, reducing the sort of complex, unreliable clustering task to a simple two-class classification problem using sort of speaker verification methods, which compare speech against a larger sample of speech to identify if the speech aligns with the acoustic characteristics of the voice print. So I'll talk a little bit about how we implemented that. So the first stage of our pipeline is transcription. And in our implementation of this framework, we used the WhisperX framework, which is very popular. It's honestly does an excellent job, especially with regards to timestamp alignment. And we use that to transcribe the conversation into phrases. So it splits the conversation into distinct phrases, which don't necessarily represent speaker turns. Each phrase can be said, several consecutive phrases may be said by the same speaker. But each phrase is said by only one speaker. So there's no, at least very, very few vanishingly small number of phrases that have multiple speakers or two speakers within the same phrase. So we ended up with a conversation transcribed for each conversation with a list of phrases. And we pass that in to sequence using chain of thought reasoning of a series of fine-tuned specialist LLM models for each of the tasks necessary to identify roles, which were, those were kind of broken into three subtasks. Firstly, summarization of the conversation. That is, so what is the nature of the conversation? In the case of the doctor and patient, this would be a sort of medical treatment conversation. Secondly, topic segmentation. I'll get into why that's necessary more later. Thirdly, role identification. At each stage, we're passing upstream information to the downstream model, providing increasingly low-level context for the task at hand. So in this case, when we're asking the LLM, what is the role of speaker one in this conversation, we're not only passing in the text of the topic segment, but we're also passing in the summary of the conversation. So it has a sense of, we're in a medical conversation, we're talking about, chest pain. The role of the speaker in this conversation and this area of the conversation is that they're expressing their symptoms. And then fourthly, crib identification. Crib just being those phrases which are clearly associated with one of the two speakers. So, and then after that, voice print mixing, where we take the audio associated with those phrases and mix them into voice print for each of the two speakers. And then each phrase is classified using the cosine similarity of the embedding associated with the audio, calculated using the wave LM large model. And then the voice print is compared to each section of speech and classified using highest similarity. And
try to wrap up, please.
Gotcha. Going back to that first conversation, here's an example applied. I'll go quickly over this, where the model successfully extracts the roles, classifies the highest confidence utterances are used to compose a voice print, which successfully diarizes the conversation. You can see down here the cosine similarity of the two voice prints successfully diarizes the conversation. Here's a technical detail, which I guess I didn't leave time for, but it's the method in which we use to generalize this to case conversations where there isn't that sort of high-level role distinction, such as cases where you have just two friends catching up, and we use topic segmentation to basically apply the same method to those conversations. But finally, we tested this out on around 100 hours of out-of-domain conversation collected from various domains of two-speaker conversations, basically found that using word diarization error rate, which sort of measures how well information is retained from the initial recording down to the actual accuracy, fidelity of the transcribed text with speaker assignment, we found that our model outperformed PNNote, which we sort of used in conjunction with WhisperX as our conventional baseline by 80%, most strongly outperforming on cases with strong speaker role distinction, but still markedly improving over on domains with weak speaker role distinction. So thank you very much for listening. If you have any questions, feel free to ask away or email me at wnehrboss@casca.ai.